Let's try that meaning again. What is the meaning of the number of protons? It defines the element. So the meaning gets us the element. Okay? Is that right? Yeah. Okay. Okay, this would get us our symbol. Okay, once we know the symbol, that could be useful because we could potentially find it on the periodic table. If we knew the protons, we knew the atomic number anyway. Okay? What does the number of neutrons then mean? Okay. I've defined the element, so by changing the number of neutrons, I'm now going to change the mass of the element. Yes, protons contribute to mass, but I've already defined that, so that doesn't change. So the neutrons are now going to define my mass. Okay? Number of electrons are going to define the charge. Just like with mass, protons contribute both charge and mass, so it contributes to both, but I've already defined the element. Okay, the instant I change the number of protons, the entire system changes, and I now have to refresh to say what element am I looking at. Make sense? Okay, which is going to take us into the next slide. Okay, element and mass. Okay, if we think about this, charge wasn't in our atomic notation. Right? It should have been. If we look at the periodic table, do you see charge specified on the periodic table? No. Charge as a concept gets kind of sidelined to mass and atomic number. Okay? Atomic number clearly takes priority because it tells us what element it is. Okay? The mass is the next big thing we report on there. Okay? That mass, if it was just the sum of the protons and neutrons, should come out to be a whole number. And when we look at the mass on the periodic table, it's not a whole number. We get these weird decimals. Okay? And what this has to do with is a kind of change in how we interpret that information. The mass number is literally the number of protons and neutrons. The periodic table will give you the atomic mass or atomic weight. Talk to a physicist if you want to fight about that. Okay? They're related to each other. They are very similar, but ever so slightly different. That difference has to do with the amount of neutrons. Okay? Carbon can come in multiple forms. I can have carbon 12. Okay? Oftentimes written this way, or we could write it out as carbon 12. What is that 12 referencing? Okay, so first thing we heard is it has 12 neutrons.
The mass number.
It is our mass numbers where we should be fishing. The backtrack from the 12 was it has 6 neutrons. That's fantastic. You're processing, but you did a lot of internal processing that perhaps the rest of the student wasn't doing, or the rest of the class wasn't doing. So if we take it stepwise, that is the mass number. What is the mass number? 12 is a fair answer to that. I do accept that. But really what I was fishing for was protons and neutrons. Because it's carbon, I know there are 6 protons. That's the periodic table, the atomic number. To get the 12, I must have 6 neutrons. So carbon 12 has 6 neutrons. Okay? What happens if I add another neutron? What changes to my symbol? Okay? 13 is a good statement. Okay? We'd have the different number of neutrons. We'd now have 7 neutrons. Did I change the number of protons? No, I just said add 1 neutron. So the number of protons is 6 protons. What would my symbol become? 13C, or carbon 13. Right?
Did you just add 1 just to humor us?
I just said let's do it. Let's see what happens. Okay? Same element, different mass. Has anybody heard of carbon-13? Nah. Okay, so let's try a different one. Instead of adding 1 neutron, I want to add 2. How many neutrons do I now have? I would have 8. Good tracking with where I was adding 2 to. And this becomes carbon-14. Has anybody heard of carbon-14? Really? I kind of hope someone would have heard of carbon-14. You ever heard of radio dating? Like, how old is this document? Carbon dating. What are we looking at? Carbon-14. Carbon-14 is radioactive. Its concentration in our atmosphere or in existence is relatively steady. Okay, as long as something is absorbing and bringing carbon-14 in, kind of like through respiration, okay? Or I ate all my food, eating, okay? So as long as a thing is living, the presence of carbon-14 is going to stay constant. What happens when it dies?
It starts to decay.
Carbon-14 is no longer being integrated into the system. But since carbon-14 is radioactive, it starts to decompose. Okay? Interestingly enough, take 152, second semester general chemistry, it decays at a very predictable rate. That predictable rate allows us to go through and be like, here's a sample, how much carbon is in it? How much of it is carbon-14? I know that thing is now 800 years old. Okay? All based off of a slightly different form of carbon. Okay? What happened? All we had to do was add 2 neutrons. Okay? And it now changes some of its chemistry. Same element, different chemistries. Dalton's laws? Anybody? Think back. Might be a good idea to star that. Be like something about Dalton, carbon-14. Okay. The existence of a second form of carbon that has slightly different properties but is still carbon, okay, now makes us say we have to refine our elements. Okay, because I don't want to have to define each of these new forms as a new element. Because if I do that, what happens to my periodic table? It gets massive. Okay, absolutely massive. So instead what we go through and do is say, well, I'm just going to report on the periodic table the average of all of the carbons. Well, if carbon always has 6 protons, what's the average amount of protons for a carbon element? 6. There's a whole number next to carbon, right? 6. That's the average number of protons for any isotope of carbon. Because it's always carbon and we can't change that, it's a solid whole number. But if we look at that mass number, it says carbon 12, or it says 12.01. It gives us a decimal value. Why is it not exactly 12? Because it's an average of the isotopes. Okay? So if we averaged 12 and 14, because those were the masses, we would get what the periodic table tells us. Just want that one to sink in a little bit. Sarah.
What are isotopes?
What are isotopes? So instead of going through and creating a new element, each with a different mass, we call the relationship between those 2 carbons isotopes. So what is an isotope? What is the relationship difference between carbon-12 and carbon-14? Different number of neutrons. Same element, different neutrons, defined as isotope. That's all it is. Okay, did anybody have a question for me based off the statement before Sierra's question?
So, just the other phrase this. So how many different elements have like different isotopes? Is the number set?
I don't know that. A lot of our elements have different isotopes. Okay, and theoretically, there's an infinite amount. Okay? But there are certain limitations behind that. Okay? So what we've encountered are what are the common isotopes.
Can you elaborate on what you mean by Dalton's law and carbon-14?
No. Not right now. If you want to talk to me after class, I can do that.
So just to verify, it's the difference between the average amount of protons and
The periodic table for mass, when it reports the mass, is the average mass for that element. So it is 12.01 and not 12 because it's the average difference. Well, we know carbon-14 exists. So what would the average of 12 and 14 be? Anybody have a question for me?
Is the electrons included in that calculation? Just the mass?
Technically, yes, but no. Okay, why would we not include the electrons in that calculation? Very, very, very small amount. Okay, for carbon with 6 protons, if we gave it 6 electrons, okay, how much of a weight contribution was it? Well, it would be 6 divided by 1,876. So 0.00000000, that's not the 0.01.
So that's the case with carbon, right? And with carbon-14. So like with even atomic mass like oxygen and fluoride, is there no oxygen 10?
They're showing decimals for a reason. There are isotopes.
But the average is like
Average, it comes out at 16. To that many, for those of you in the Tuesday lab, this sequence of words will make sense. Those of you in the Thursday lab might make more sense after today. It should make sense to all of you because you watched the play posit. They've reported 4 significant figures. Could we have 5, 6, 7? Yeah. Okay. I don't know the exact precision on these, but we can pull out at least 10 places would be my guess.
What is the sample size?
If the average of carbon-12 and carbon-14 is 13, what should be reported on the periodic table? 13. What do you mean sample size?
Carbon 12 to 1.
The average, they're obviously not taking a human, right? Unless they are.
They're saying across everything to an approximation. So we have to have some approximation there. So that's a slightly different system. When we take the average to get 13, what did we assume? 12, 112, and 114. Which says we're assuming when we look at the element of carbon, there are 2 isotopes. 50% of those isotopes are carbon-12. 50% are carbon-14. That's how we would get an average of 13. Was that assumption true? No, because the periodic table tells you it's 12.01. So there's something wrong with how we calculated that average. Okay? Carbon can be trickier, so let's take a backtrack away from carbon and let's shift to hydrogen. Okay? Hydrogen, we actually name its other isotope. We call it deuterium. Why might we name hydrogen's isotope? It's not a compound, it's still an element. Why might we name that?
Changes the use of
Carbon-14 versus carbon-13 or carbon-12 had different uses as well. Why would we name that element?
there's not a lot.
Getting at an amount is going to be part of it. Okay. What is the relative amount of hydrogen-2 in comparison to hydrogen-1 in comparison to, say, carbon-14 to carbon-12? Okay. Maybe there's a larger amount of hydrogen-2, which is why we'd want to name it. So we don't have to refer to it by the kind of silly-sounding name of hydrogen-2. Okay. Hydrogen is our simplest element. Right? So we tend to do a lot of models based around the simplest thing. Why?
It's simple.
Because it's easier. Okay? So when we look at hydrogen, we studied it a lot more, and we start to look at all of the common forms of it. Okay? Because we study it so much, there's a larger body of knowledge on it, and we start to name things so that we can stop sounding like weirdos by calling it hydrogen 1 and hydrogen 2. Instead, because scientists like to do this, we want to feel cool and special and fancy, and we say we have protium. So, oh, what is that? It's just hydrogen. Okay. We have deuterium. Oh my God, that's so cool. What is that? It's just hydrogen. Okay. We invent these new terms to make it sound cooler. Okay. I'm sure they have other reasons behind it too. But I base a lot of science off of making it sound cool. Okay? So, what is the origin between these two names? What is in a hydrogen atom? Okay, and because we said this was actually nuclear notation, what is in a hydrogen nucleus? One proton. One proton and one neutron. You're holding up a big giant 0. Why?
How does it have a mass of 1?
The mass is 1. What is the mass of one proton? 1. If I add a neutron, what happens to the mass? It becomes 2. So if we're talking about hydrogen, okay, and in particular protium, how many neutrons does it have? 0. So what is in a protium nucleus? One proton. What's the name we gave it? Protium, because all it's got is one proton. That's where the name's coming from. What happens when we move to deuterium? Well, it has a proton and a neutron, so we could call it pronudium. And you laugh. Exactly right. They were like, that's a dumb name. Let's try something else. Okay, what name do they pick? Deuterium. Why? Try that again. A mass number of 2, meaning 1 proton, 1 neutron. It's still hydrogen. I can't change the number of protons. Okay? But there's 2 things in the nucleus, so I'll call it deuterium because there's 2 things there. Okay? Deu for dual. Deuces. Just let that one slide. Like when you're playing poker, right? Okay? If we now look at hydrogen and we want to determine its atomic mass. So now what we're saying is I want to report what's on the periodic table. Don't look at the periodic table. Stop it. And I want to report the average mass on the periodic table. Okay? Well, I know deuterium has a mass of 2 and protium has a mass of 1. So if I'm going to obtain an average mass, what do I do? 1 plus 2, the individual values, divided by 2, which was? I know where you're going with that, but try again. What's the 2?
Oh, it's the number.
The number of things that went into your sample. Okay, this would be your sample size, which is where I thought you were going. Okay? And we get that, we get a number of 1.5. And so when we go to the periodic table, we can prove how awesome our calculation is because the periodic table will tell us the atomic mass for hydrogen is 1.5. No. Okay? So what went wrong? Does that mean our calculation is wrong? Really what this stems from is what did we assume when making this calculation? We assumed an equal percentage of protium and deuterium. We assumed there was 50% protium and 50% deuterium. Where in that calculation do you see 50%? Okay, it's not there. I will challenge that assessment. We're going to have to rewrite some stuff though, get that up a little bit higher. Okay, because this is magic. Dun, da, 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 right? Magic. And I said 50% is actually in that equation.
Yeah.
So here's the magic start. Is that valid?
All those synonyms.
We said 50%. 50%. What's per mean? Per does not mean out of 100.
For everyone.
Per means division. What is cent? We assumed 50% and 50%. Was that assumption valid? No. Turns out we're actually pretty far off. Okay? How much protium is there? It's about 99% protium. And it's about 1% deuterium. Show the calculation. Write it down. Show the calculation for the average mass now. Bit of a dick move because I just erased that work, but if you were taking awesome notes, guess what? It was already written there. If you got questions on this, which is an awesome step, pushing out the percentages. Those percentages need to get written out. I saw him write 50 per 100 and was like, he did that. I did. What does that equal? 1. What's the mass in the periodic table? 1.01. So while that is perfectly mathematically valid, that is not what we were asked to do. We wanted the average mass. What did we write so far? Just the percentages. What are we missing? The masses. 99% for the mass of protium, which was 1. 1% for the mass of deuterium at 2. Now when you punch in your calculator, guess what you get? 1.01. Look at that. What's even more amazing about that is the first time I did this, I just guessed at what the percentages were. I honestly didn't remember. Okay? Does that mean hydrogen only has 2 isotopes? No. Okay? We could have a bunch more isotopes. We could have 2 neutrons. Okay? How many things would be in its nucleus now? 3. So we could call that threum. Ooh. Too many vowels. Tritium. That fancy magical thing that we hear, is this whatever it is, and all the sci-fi. It's literally hydrogen. Okay? That's tritium. Why do we call it tritium? Tri for 3 things in the nucleus. That's where it's coming from. Okay? So what we just accounted for here is how we calculate atomic mass. The periodic table tells you atomic mass. Atomic notation tells you mass number. If you average the mass numbers for all of the isotopes, you'll get the atomic mass on the periodic table. Okay? What we're looking at are percents, which is why I had you double back and read early on in one of the earlier chapters about percents. That was the whole point. Okay? How do you guys feel about percents? Are you okay with just normal percents? Yeah? Okay, then we'll just kind of gloss over that. If you got questions, you can talk to me after class. What those normal percents are, what I'm calling normal percents, are really simple averages. Okay? Or simple percents. They aren't super complex, and they've embedded a lot of kind of the more advanced calculations into the background so you don't see them. Okay? What I would reference that as my voice goes in and out, is an algorithm. Okay? I know I'm going to calculate lots of percentages, so I'm just going to do it this way. Okay? It's easy. I just punch in numbers and it works. Okay? The weighted average is the larger step back, can now apply to everything. Okay? So it gets us a little bit more breadth and depth to be able to do multiple different things, as opposed to just a single thing, a single action. In a job, what are you going to be expected to do?
Your damn job.
We can do a little bit better than that. A single thing. Okay? If you go into the job and only do that single thing really well, that's fantastic. You may get paid for that. Guess what happens when we build a computer that can do it faster than you? You're gone. Okay? So what you need to be able to do is not learn how to do one task very well, but be able to take a step back and say, how can I do it better? Okay? How can I integrate that concept, those pieces, into a larger context so that now, if someone comes to us and says, we got a computer that can do that for you, you can be like, oh yeah, make the computer do this. And they're like, okay, we'll hire you back. And that's when you now have the, but I'm now doing more for you. You need to pay me to fix that or I'm walking away. Right? So you want to be able to understand the entire process, not just sit there and flip burgers. Right? Because if you know every piece, you can now contribute to a larger level and it becomes harder to get rid of you. Okay? That's what I want you to go through and do with the chemistry class. I don't want you to memorize a specific task to get through something. Okay? And this is a common complaint that I get from people. But I was told I could, this equals this and times this, and I just solve it and I'm done. That's fantastic. What happens if I ask you this question? Well, I don't know how to answer that. If you listen to how I asked you to solve the question, you would. And instead, you found a shortcut to do an algorithm that solves that one question very fast. So virtually everything I give you makes you solve things slower, but allows you to solve all things, not one. Okay? Really think about that when we approach topics. So if we go through, our weighted average, okay, is multiplying our percentage, okay, by the weight of the object. Okay? And then we add all of those up. So if I ask the question, gallium has 2 isotopes, gallium-69 with this weird mass, well, I don't care about the units necessarily, and that abundance. Okay? And it has this isotope, gallium-71. What is the mass of gallium-71? Okay, careful. Gallium-69 has a mass of 68.926 AMUs. Okay, we're adding more sig figs into this, so we have to be a lot more careful. I'm not asking for the mass number. I'm asking for that element mass. We get a slight variance in the numbers because of units and sig figs and stuff. Okay, so I want to know its exact mass. How could I go through and do that? I wonder if Mike just gave me a tool that would allow me to go through and process that. I mean that tool where it was the percent of one thing times the mass of that one thing plus the percent of another thing times the mass of that thing. And that when I added all of those up, those equaled the average mass or our atomic mass. Lots of moving pieces. We went from, oh yeah, I understand percentages to, oh crap. Okay. How easy is it going to be to confuse 69 with 68.926? Very. Throw in 71. Yeah, it could be really hard. So maybe what we do is instead of thinking about these by all those numbers, is make this red gallium. I didn't want red, I wanted blue. Doesn't really matter. Okay. That red gallium had a mass of what? Did it have a percentage? Then what else was I asked? What other given information is in there? I know that I have a second isotope, gallium-71. Do I know its mass? Do I know its percentage? Okay, so there was a mix of yeses and nos there, which is fantastic. So let's approach that in just a second. What are we being asked to solve? I need to know the mass of red. Okay, that red box has to be solved for. To solve for that red box, what do I need to know? What number goes there? What number goes there? What number goes there? That is one variable. I like the pointing. Stop it. Okay? One variable, one equation. Okay? I have to know all of those other values. So the question now becomes, do I know those values? This is where the color coding can come in. 68.926 we said was the AMU, and it says mass, right? So what could I do? 68.926. Color coding with the blue as well, 60.11%, which means I have that first value, 60.11%. What goes over that 100?
111 minus 100 minus.
Okay. This is why I was a bit shocked. The yes crowd was very, very loud, and then the no crowd was like, wait a second, hold up, and started to come back in. Okay. For those of you that said no, it's not explicitly given. Okay. So saying no was okay. However, it is implied in the question. You were told that there are two isotopes. If one of them is 50%, what's the other one? 50%. How do you know that? Percent. It's out of 100, right? With only two things, what do I want? I know that the percent of the red one and the percent of the blue one, when added together, must equal 100%. Okay? So if I want to know what the percent of the red one is, I can take 100 minus that blue one. Yeah? Okay. Up to you where you want to do that calculation. You can run it as a separate calculation on the side, or as William was suggesting, take 100 minus that percent and drop it right in the middle. Okay. Either one's going to work. Okay. Because I don't think I have enough space to drop it in there. Sorry, William.
That's fine.
What was our number? 39.89. Thank you. I can now put that 39.89 into there. I'm just going to write mass, because I still don't know that. But I need a number for atomic mass if I'm going to solve this. Okay, another pointer. Jeez. Lots of pointers. Okay, it's starting to get better. Okay, because you're all starting to be like, well, where was the atomic mass found? The periodic table. That is given information. In this question, does it say look at the periodic table? Why are we allowed to assume you're to look at the periodic table? Because you're chemists. And you own a periodic table in your pocket at all times. You're like, that's crap. That's not true. Do you have a smartphone? You have a periodic table in your pocket. As far as for a test, you have the two periodic tables on the wall, and I give you one on the exam. Okay? So we pull up the periodic table, our atomic mass, where did the number go? 69.72. Now what can we do? We can do our calculation in the algebra. Okay? This is another common complaint of students about me. I'm not going to solve the algebra. Okay? If you want that, I will absolutely do it with you, but I'm not doing it in class. Okay? That's it. Does that make sense? Okay. So we got a lot of floating questions out there. Because you all just exploded with questions. Are you guys resolved or do you need help?
Oh, I was just explaining how you,
Where we got?
where you got the percentage from, how you did the difference.
Oh, okay.
Yeah.
This one.
I was just,
Are you guys good?
yeah.
Christian. You are absolutely allowed to use a calculator, and as I said on day one, what should you do? Get one and bring it with you every single day. Okay? That way, when the exam comes, it's not, oops, I forgot to bring it that particular day, because you always bring it with you.
But do remember, you're not allowed to use the app on your phone.
Yeah, you can't use your phone. Yes, Andre.
So, when you get the mass off the periodic table, do we put a 0 behind that too, because we're taking it to the...
So, I kind of interrupted you. You don't add a 0 to it because the periodic table doesn't say 0.
Okay.
Okay? The question where you were starting to go is the statement for significant digits. This is a holdover from when I taught sig figs early in the semester. Don't stress. Okay? We'll talk about that again. I'll try and remember to bring this example back up when we actually talk about sig figs. 69.72 is for sig figs. If I add a 0, it's now 5. Okay? So you should be able to go through and get a number. That number is going to be somewhere in between 69.72 and 71. Yeah. Okay, someone actually calculated it, so I'm not going to show the work. But what was the number? 70.92. Okay? Kind of, sort of? Okay, so you want to memorize a formula? Great, you can memorize that formula. Okay, do you need me to box it so you know? No. Yes. Okay, I'm going to do it a different way. I'm going to erase stuff so you know. Don't say don't do that. I already erased. Shh, I'm going to do that in a second. Okay, there's our formula. You should be committing that formula to memory. That said, this is now kind of an algorithmic thing. How big of a fan am I of algorithmic things? I said a horrible fan. Algorithm things allow you to do one thing and one thing only. That's not good. Okay? So how many times do you think you would expect to use this? Probably like once. Out of a question of 40 things, are you like, God, these numbers are hard, I don't want to deal with them? Lose one question. Okay? So, cool stuff. Periodic table. So let's take a look at the periodic table. What the hell is that? All of those are periodic tables. Okay. So a really good question that's coming out of this is why? Why would you do this? The only one that I can easily explain why for is the very first one. You're like, that's some weird LSD thing. Elements, according to, calm down there, to relative abundance. Okay? So the bigger the symbol, the more there is. Okay? Why would I want to use this periodic table as opposed to the one on the wall? Because I care about what elements I need to work with. I might be like, I want to make something new, but I want it to be as cheap as humanly possible. I'm not going to pick something that has virtually no abundance because that's going to be very hard and expensive to get. Okay? So looking at abundance could help me with that. Really, I don't think anybody uses that, to be honest. But that would be a reason why we could shift to that. Okay? The other ones are organized for different reasons. Those reasons, I believe in both cases, have to do with where electrons are located in the nucleus. Okay? The periodic table on the wall also tells us where, sorry, not in the nucleus, where our electrons are located. That information is encoded there. Okay? So one of the things that we will have to do is to share with you the code so you know how to find that information. So that when it gets to the exam, you just have to decode it and tell me what that answer is. Make sense? Okay? So we have to use a writing system to allow us to interpret this information. You have to be taught that system. If you don't know that system, it's all Greek. Like, that's a different language. That's the point. Okay? So, classification of the elements. A little bit of history here. Don't stress about these names. I just think these are neat. Dobereiner, 1830s, goes through after Dalton does. He says, you know what? I think we can organize those elements a little bit differently. And he groups them according to triads. Why might we consider triads? He spent a lot of time in Asia. Some people got that. If you don't worry about it. We'll try a different one. Okay? He was very religious. Father, Son, Holy Ghost. Okay? Humans will look for patterns. Wherever patterns have been established before, we will try to overlay those same patterns on top. That's a very likely case for that. If we look through the periodic table now, do we see groups of threes? No. So what the hell was he smoking to get three things? Did we have, that one's like slowly grenading out there as people are like, oh, I think I get that. Oh my God, I really get that, yeah. We didn't have all of those elements discovered yet. We're still 1830s, okay? So with a limited amount of elements, he's going to start to only see simple patterns, okay? Those simple patterns weren't elaborated on until we get more elements. 1865, Newlands goes through with 62 elements, and he groups them according to 7 according to atomic mass. Okay? Interestingly enough, our periodic table does have groups of 7, which I was going to draw on the periodic table on the screen. It's not there. And that's not helpful either. Well, yeah, I'm not going to do that. Our groups of 7 have to do with kind of the discoveries. 1, 2, 3, 4, 5, 6, 7. You're like, dude, what about 8? Or like this entire freaking middle section. They hadn't resolved enough of the entire middle section, and they ended up misclassifying those into the other 7. What happened to 8? Those are the noble gases. How many of you know someone in the nobility? Exactly. Same issue. Those gases avoid virtually everything. Okay? They're noble. They don't interact. They're very hard to discover because they don't interact with anything. Early on, we don't have access to that row because we don't know that they exist. Okay? His theory was called the law of octaves. Coming from music. And you might be oct 8. There were only 7. What the heck? Apparently music repeats on the 8th, and that's why they call it an octave. Oh, yeah. Okay? Again, searching for patterns. We found patterns in music, so of course, Earth and nature must be organized according to beauty of music. Right? So we were trying to overlay what we already knew to build forward. Okay? Then we get a crazy Russian dude. Read about him. Why are they all Russian? Because the Russians were crazy enough to study? I don't know. Mendeleev went through, and he organized according to increasing atomic mass too. And you might be like, well, that's not that big a deal. Didn't Newlands already do that also? But here's where Mendeleev proved his craziness to not be so crazy. If we take a look at his periodic table here, we see these weird ekas. Like, symbols don't repeat, and yet eka repeats? What are you talking about? Eka just means similar to. Meaning, there wasn't anything there. Mendeleev said, dudes, there's an element there that you haven't found. That is eka aluminum. It's similar to aluminum in its properties. Go find it. Okay? Eka aluminum 2. I don't know. Why not? Okay? Eka titanium. I know there's something out there. So his periodic table not only organized them, but he was able to organize them and be like, there's a gap. You dudes suck at chemistry because you haven't found this. Go find it. That's pretty amazing. Actually, that's not that big a deal. I could be like, in 20 years, you're going to weigh 119 pounds with a body fat percentage of 15, and you're going to be like, you're full of crap. But if in 20 years that turns out to be true, you're going to be, what the hell did you do? That's what happened with Mendeleev.
Did he figure these gaps because of the changes in mass?
So he was able to look at varying properties of the elements to predict that something else had to be there. So he could probably see the properties of aluminum and yttrium being the same, but their mass differences were astronomical, say in comparison to magnesium and strontium. So because of that, he postulated something had to be there.
Or just left the opening for possibility.
Yep.
Do those patterns hold up as you go through the...
If we go through and take a look, ekasilicon, predicted in 1869. Germanium, so the actual element, was discovered in 1886, 30 years. And remember the example I gave. In 30 years, I'm like, you're going to weigh 115 pounds? That seems kind of low. Well, maybe that's high for some of you. I don't know. Okay? Have a body weight percentage of 17.64% and have orange hair. You'll be like, you're an idiot. Gray and gray. Oh my God. All metals are freaking gray, so that's not that big a deal. Okay. Atomic mass, 17 versus, or 72. 72.16. Just because I can't read, don't make Mendeleev look like an idiot. Okay? That's pretty ridiculously close. Okay? Remember, this is 1869. When was an electron discovered? 1900. Density. Remember I said that body fat percentage? What? That's pretty freaking close. I'm going to add one more prediction here, just to kind of jump. You will also be married. The combined body fat percentage of you and the spouse that you have yet to meet will be 32.1. When ekasilicon reacts with chlorine or with oxygen, its density, I predict to be 4.7. It comes out to be, what? Seriously? This is a 30-year gap in time that he's able to just arrange the elements and be like, yeah, that's what it's going to be. That's pretty freaking intensely cool. Okay? This is one of the reasons why we give Mendeleev a lot of credit for building the periodic table. Okay? His periodic table had a lot of gaps. He also made a lot of predictions that were horribly wrong. But as with most science, we look at the things that were successful, not the failures. Okay? It was then refined a little bit later. And instead of going by atomic mass, we switched it to atomic number. Okay? Instead of atomic mass. So that's why we see the atomic number at the top of each of our elements, not the atomic mass, because the atomic number is a better descriptor of the organization. Okay? With that, we'll go ahead and stop, and we'll pick up there